De gravar. Ok. Perfeito. Não, não, que?
Λοιπόν, καλησπέρα. Happy New Year, everyone. Welcome. It's really great to see you all. Sorry we're starting a little bit late. So I'm really excited to kick off this new year with all of you. We have a very nice lineup of events coming up. We're going to start meeting up once every month. And I want to talk to you very, very briefly, because I know we all want to hear Ismud and Epheriel talk to us about their wonderful tech. Okay, I want to talk to you very briefly about some of the goals I have for this year. I am trying to build this community and really bring in speakers from academia, from startups, and from larger companies, and I'm in talks with many people. And I want to invite all of you to help me on this great journey. I think we're doing really well. We're nearly 600 members. I'm really excited to see that. I'm also really humbled by all the interest that many people have expressed, from researchers, from industry. There's an overwhelming amount of support from companies, both large and small, in our meetup, and I think this is going to be really good for us. From larger people like O'Reilly, who are going to start offering us discounts on their content, as well as discounts on their various conferences that they have, which I think is really good. As you know, we have a website in the works. The website does have a few hiccups in it. It's not completely ready. We are in the process of trying to get this finished and really polished so that you can all access the content. And I know a lot of you have asked me, where are the slides? Where is the videos? Everything from all our past meetups and this one and future meetups will be going through there. And in fact, one of the things, and I know various people have talked to me about this, one of the things that people have suggested is I try and grow the leadership team. We try and grow the people who are actually managing the meetup, because we're at the point where we have a lot of interesting things we want to do. I want to grow our social media presence. I want to also promote us with various different companies and get more speakers. One thing I want to ask, and I want to get some feedback from people, is slowly I will send out a poll for you to complete in the kinds of events, kinds of activities that you would like to see. I would like you all to participate in the direction that this meetup is going to take over the year and moving forward. And I also want to invite especially people who writers and designers who would like to contribute to the website, to the content that we create. Please message me through the site. Please contact me so that we can see if you can actually contribute. Beyond that, to kick off our wonderful meetup, I want to thank our sponsors again. I know I say this every time. The sponsors really are the big reason why we're able to meet here and build this community. This time we have Paulfish, who are going to sponsor the food and drinks, which I know we're all huge fans of, and sort of pizzas later on. For sure, you've all heard of Paulfish by now, right? They spoke last December about their technology, and I hope they'll come and speak again. At the same time, I also want to thank Alba, who has very graciously contributed to our meetup by allowing us to meet in this amphitheater. I've had the very fortunate opportunity of actually lecturing at Alba as well in some of their master's program. They're really good. If you are interested, do check them out. And that's pretty much all I want to say. One thing the organizers have told me is that apparently the tables outside on which the pizzas will be arranged are not industrial strength, so please do not try any acrobatics on them. I don't know, they just felt I should mention that. Beyond that, I'd like to welcome Anna Kasimati from Izmut, and I'll leave it up to you there. Thank you very much.
Hi, hello everyone. Thank you, Miguel, for inviting us here. We're very happy to participate in this meetup. I will tell you just very few things about Izmut. Izmut is a startup company operating in the field of social network analytics. And what we do is that we collect and analyze data coming from various social media and online sources in order to answer three basic questions. Who is talking? Who is speaking for a brand or a person? What they are saying, which are the topics they discuss on, and how they feel. And this is where sentiment analysis comes in. And this is what our technical people will talk to you now. That's it. So Stavros, our software engineer, and Sakis, our CTO, will give you more details on how we have addressed the challenges of sentiment analysis in Izmut and what we have achieved until now.
Good evening. This talk is entitled Sentiment Analysis, a Hard Pattern Classification Task. So within the next few minutes, I will try to justify our title. My name is Dionysios Sotiropoulos. I'm a co-founder and CTO at Izmut. I received my PhD in machine learning from the University of Piraeus several years ago, and currently I'm a postdoctoral researcher at the Athens University of Economics and Business. Let me begin with an overview of my talk. Firstly, I'm going to give you a broad description, a very abstract definition of the pattern classification problem and the associated workflow, which is usually employed in order to tackle any pattern classification problem. Subsequently, I'm going to focus on the machine learning paradigm of learning from examples, which underpins every training process of a machine learning classifier. And then I'm going to give you a definition of sentiment analysis within the context of pattern classification and machine learning. Then I'm going to analyze the reasons for which we believe that sentiment analysis is indeed a hard pattern classification task, and especially the sub-problems that one needs to address in order to solve the bigger one. These sub-problems relate to the corpus vectorization process. We strongly believe, and this is the truth, that sentiment analysis is a highly imbalanced pattern classification problem, which we will try to address through the paradigm of support vector machines, which we actually benchmark against a series of other pattern classifiers. So I will conclude this presentation by providing a comparative study of sentiment classification with various machine learning techniques available. So, fasten your seatbelts, and some definitions are on the way. What is pattern recognition? Pattern recognition may be defined as the assignment of a physical object or fact into one of many predefined categories. What is a pattern? A pattern is an object, process, or fact that can be assigned a name. A class is a set of patterns that have some characteristics in common, usually originating from the same source. And a classifier is a machine that automates the process of pattern recognition. Pattern recognition is the process which is employed by your brain every time it needs to classify a particular visual stimuli as originating from your mother's face or any other face. In that case, your mother face is the class under the various luminal conditions that you may observe this particular face, and the pattern, the feature vector, is the stimuli that eventually reaches your retina. So the pattern classification process is what? To recognize the face of your mother against any other given face. So the general workflow, which is usually followed in order to address any kind of machine learning problem, is the one appearing on the figure on the right-hand side. The first step is the data acquisition and sensing process, where we perform measurements of the physical objects that we need to classify. The next step is the pre-processing step, which is usually focused on removing noise from the data and isolating the patterns of interest from the background. The next, and which is the most important step, is the feature extraction phase. This is where we do the actual mapping from the physical world to the world of mathematical formulation and mathematical representation. It is the one step where a physical object acquires a particular mathematical representation in a given vector space, usually a high-dimensional vector space. Classification is the process where we utilize the extracted features in order to train models that automatically perform the aforementioned classification task. And finally, post-processing is the process where we evaluate the classification process of our classifiers. We evaluate how good they do the job for which they train them. So, in order to address difficult pattern classification process, we usually rely on the so-called learning from examples machine learning paradigm. And which are the fundamental components of this paradigm? First of all, I want to mention that it is a model that addresses the problem of functional dependency estimation. And the main components of the model is the data generator, G. This may be the nature. The target operator or supervised operator, which assigns the class label on the given input vector. And finally, the learning machine. This is where we intervene and we provide an estimation for the actual class label. So providing an estimation which is close to the actual state of the world is when you do this problem, when you address this problem in good terms. So the data generator serves as the main environmental factor which generates the independently and identically distributed IID random vectors x and y, x and x, according to some unknown but fixed, this is very important, probability distribution f of x. And these random vectors are subsequently fed as inputs to the target or supervised operator, which finally returns the output value y. It is important to note that there is no information beforehand concerning this transformation of the input vector to the output values y. This is what we are trying to learn, so there is no information. the only available information is that the target operator exists and does not change significantly over time. Here is a figure where you see a target, an input vector, a feature vector, which is usually represented in an n-dimensional vector space, associated with the corresponding hidden state y in y, and patterns with equal hidden states pertain to the same class. So, what we have said is that the only available information is that the corresponding target operator exists and does not change. And the fundamental assumption behind the machine learning paradigm of learning from examples is that the supervisor, the output value y in x, according to some unknown conditional distribution f of x, f of y, including supervisor that forms a single mapping. So, the goal of the learning machine, the goal of the classifier, is to provide an appropriate approximation, g of x, for the joint probability function f of z, f of x, comma, y, but this approximation can only be implemented on the basis of a given training set, a set of feature vectors which we know beforehand the associated class labels. In this context, the problem of machine learning may be reduced to the problem of searching for an appropriate approximation function within a given set of functions, which are usually parameterized by a parameter alpha. So this alpha might be the weights on the space of linear functions. More formally, the problem of machine learning may be reduced to a minimization problem. Do not mind many mathematics. The main notion is that the underlying minimization problem tries to minimize a quantity, which is the probability of a classification error when the joint distribution function is unknown. The only available information is the sequence of L training patterns. An important work from Vapnik in 1995 reformulated this problem of machine learning by replacing the actual risk functional, the one with the integral, with the empirical risk functional, defined in this situation. And the empirical risk functional counts the number of classification errors strictly on the training set. So we are trying to build learning machines which operate by minimizing the number of mistakes that are committed within the training set. As I mentioned before, we will try to formulate the problem of sentiment analysis within the context of pattern classification. What is sentiment analysis? Sentiment analysis is the computational study of opinions, sentiments, subjectivity, evaluations, attitudes, appraisal, effects, views, emotions, and etc. All of these expressed in textual form. So, sentiment analysis within the context of pattern classification may be reduced to the problem of defining a mapping from the set of documents D to the discrete space of classes which correspond to the categories of positive and negative sentiment. It is indeed a very hard pattern classification task, since it spans a broad spectrum of research fields which are associated with extremely complex sub-problems. Can I have some water? It's too hot. So, I'm going to provide a step-by-step approach in justifying our initial statement that sentiment analysis is a hard pattern classification task. Okay? So, the first step, sensing, which relates to the process of data acquisition, is an easy step because you can do it by applying keyword filtering. The next step, the segmentation step, where we are trying to apply some noise reduction and noise removal techniques. This step can only be achieved by performing a sequence of data cleansing operations for noise reduction purposes, which all these are natural language processing related tasks. Tasks such as tokenization, stemming, lemmatization, and stop word removal. More details on this tab will be given by Stavros within the second part of our presentation. So, the most difficult problem that one faces in order to perform sentiment classification deals with the feature extraction process. As we said before, with the process where the physical objects, documents in this particular case, acquire a mathematical representation. And what is the challenge here? The challenge here is to be able to acquire a mathematical representation of the unstructured textual information. Usually textual information is considered unstructured. Why? Because you need some mathematical space in order to map the documents or the tweets or any kind of post that is available on the web. So one has to address these two mutually exclusive or competitive tasks. The first task is to be able to provide an efficient low-dimensional representation of a given corpus, because low-dimensional feature representation means that you can create a classifier with a sufficiently small training data set, whereas an efficient representation of unseen documents requires feature spaces of higher dimensionality. So when you decrease the dimensionality of the feature space in order to acquire a higher classification accuracy and an easier classification task, at the same moment you increase the probability that an unseen vector will fail to be represented within your dictionary. Concerning the classification process, it is true that the problem of sentiment classification is an extremely imbalanced classification problem. What does this mean? It means that the class of positive sentiment is heavily underrepresented within the social media. This means that the majority of the posts are negative. We have some more water. Sorry.
Okay, if that runs out, I will run out to get this.
Okay. It's too hot in here.
I've asked them to turn on the heating, so this is getting progressively closer to the room temperature.
Okay, so we have mentioned that one problem is the class imbalance problem, and another one is the problem relating to irony. Irony contributes to the class separability problem, since the presence of such figurative language works as an expected polarity reverser. What does this mean? When you have your feature space, a positive pattern, in the case of irony, is located within the boundaries of the negative class, and vice versa. Therefore, there is a region within the feature space where it is equally probable for a pattern to originate from the positive or negative class. And finally, the final step, which concerns the evaluation of the classification accuracy of a given classifier, is an easy step. It's a standard step which is usually addressed by realizing a tenfold cross-validation. Can we make a break? I think
We can.
yeah. I don't think I will.
All right, let's take 5 minutes. Okay.
Ναι, άμα μπορεί.
Μας ενδιαφέρει πολύ αυτό. Δεν φαίνεται καλά να κλείσω διάφραγμα. Δεν φαίνεται το πρόσωπο του μιλητή όμως. Το πρόσωπο του μιλητή μας ενδιαφέρει περισσότερο. Ωραία, άρα τότε να κλείσω διάφραγμα εδώ. Όχι ρε φίλε, στην άλλη γράφει, γιατί έτσι.
Let's cut it up properly. I explained in terms of the workflow steps that one needs to follow in order to address the pattern classification, any pattern classification problem. Sentiment analysis is such a problem. But sensing is not a difficult subtask because it's concerning our measurements. The text documents are collected as they are. There is no noise in this process. We may need to afterwards to subsequently remove some of the words or of the terms because they are irrelevant to the sentiment classification process, but we have no noise from the data collection process. The data, we consider that they are the data integrity is not jeopardized. This step. The segmentation process is a critical one where we need to perform some text normalization techniques, and then we were at the feature extraction process. This is a very, very difficult task, and as I mentioned before, one needs to simultaneously address two competitive, mutually exclusive tasks. So each document, it needs to be represented as a point in a multi-dimensional vector space. This is the only way any machine learning paradigm, any machine learning algorithm can work. You need to have a mathematical representation. But how can you obtain a mathematical representation that is unstructured as text? The answer to this problem was provided by the standard, the so-called standard vector space model, where each document D in some corpus, D capital, is represented as a vector containing only the words that belong to the document and their frequency by utilizing the so-called bag of words representation. However, this representation loses any information which relates to the punctuation, order, or grammar information of the sentence. So it is a way that you can mathematically represent something that you would hope to mathematically represent, but there is a catch. You lose information concerning punctuation, order, and grammar. So, how the corpus vectorization process works in very abstract terms. So, not follow the equations, just try to follow what I'm saying. The main notion here is that given a sequence of documents, we have a corpus of documents, and after applying the processing, we complete collection of terms. It's just like having a dictionary of all the words you can encounter in a given corpus or in a given language, the Greek language or the English language. So suppose that you have this dictionary of terms, that will be M terms.
each document is then represented as a vector with m elements. M elements equals the number of the terms in the dictionary. So each term fires on when a particular word of the document, when that particular word in the feature vector appears in the document. However, this on-off situation in the feature vector is weighted by a weighting scheme, which is the so-called TF-ITF weighting scheme, the term frequency inverse term frequency weighting scheme. What I want you to remember is that each document is actually represented as m values, and the non-zero values are these words that appear on a particular document. However, this representation based on unigrams, as we mentioned before, loses all the local ordering of the information in a given document, such as a document containing interrogative form. You lose these syntactical structures of the sentence. A possible remedy for this problem is to utilize the so-called n-gram-based corpus vectorization process, which usually involves a significantly larger dictionary of terms, where at this time each term is actually a sequence of n terms that you encounter in consecutive order within the documents of the given corpus. However, this n-gram-based corpus vectorization process results in extremely sparse feature spaces. Sparse means that the corresponding feature vectors, the large majority of their elements are zeros, and that most of the terms are meaningless sequences, which are highly weighted due to the IDF weight. So you see that you're trying to solve a problem, and there is a remedy for that problem, and then a bigger problem arises. So it is a hard problem to address. So we say that sentiment analysis is a hard pattern classification task, which is significantly hampered due to the inefficiency associated with the underlying feature extraction process. That is, a new document may acquire a zero-value vector representation if none of its terms pertain to the original dictionary. And this is because this corpus vectorization technique, and any corpus vectorization technique, is a corpus dependent. It depends on the given corpus that you want to represent, so that a new document may acquire a zero value representation. If I hear someone talks to me in Chinese, I will try to search my dictionary and I will not find these words. So the internal representation of what he's saying, it will be a zero value representation. So not only can I assign a sentiment value, I can nearly understand. Okay, I can understand what the other person is talking about. So efficient representation of unseen patterns may achieve by considering high dimensional feature spaces. But as you increase the dimensionality of the feature space, you need, in order to train efficiently a classifier, an exponentially larger number of training instances, and this problem is usually referred to as the curse of dimensionality. And another very important and difficult problem to address earlier is the class imbalance problem. The class imbalance problem is encountered by inductive learning machines, as the one that we are talking here today, when the assumption concerning the similarity of prior class probabilities is grossly violated. That is, the ratios of prior class probabilities are extremely skewed and arises on domains for which the target class of positive patterns or positive sentiment is heavily underrepresented in comparison with the complementary class of negative patterns. And it also arises in cases where the target classes are assigned with highly imbalanced misclassification codes. Suppose that I say to you that you are going to take an exam where there are 1,000 questions, yes, no questions, and one answer is no. One of the 1,000 answer is no. What's your best strategy in order to tackle this problem? That's the correct one. If you answer correct to anything, you are most probably to do one mistake over 1,000. So you will be 99.99% correct. And this is what happens with the learning machines. They are significantly biased towards the majority class. Okay, let's skip this one. So, as we mentioned before, the sentiment analysis problem is a highly imbalanced pattern classification problem because, according to our experience with Eastman, we have observed that the majority of the posts are indeed negative. Most of the people express themselves negatively or against someone, something, or a brand. They have the incentive to be expressed in textual form for most cases when something is wrong rather than when something is right. And this problem may be alleviated by two major techniques. One is that you may apply majority undersampling in order to balance the training dataset, or cost-sensitive training, that is to assign a higher misclassification cost for the instances of the minority classes. And then I'm going to give you some details about the support vector machines. Support vector machines have been presented in the literature by Vapnik in 1995, who was a mathematician, who is a mathematician, and are nonlinear classifiers that operate in higher dimensional feature spaces than the original feature space of a given dataset. Their training process involves a quadratic minimization problem in the context of a binary classification task, which finally results in an optimal set of parameters. The important thing here is that quadratic minimization problems have overall minimums, overall optima, in contrast to other machine learning techniques such as neural networks, where they may be trapped to local optima. So the solutions that are acquired from the support vector machines do with the global optimum. So having determined these lambda parameters, it's like you have determined a hyperplane in a high dimensional feature space. Suppose that your feature space was two-dimensional, that you only had two features, var1 and var2. Determining these lambda values is identical to determining a line which discriminates the class of positive patterns, the class of positive sentiment, negative sentiment. The main idea behind support vector machine is that, as you can see, there is a multitude of lines that can solve this problem, discriminate the class of positive sentiment from the class of negative sentiment. The main idea behind support vector machines is to be able to determine the one to which I'm pointing at, which maximizes the margin between the positive class and the negative class. So the minimization process, what I said before, it's trying to identify this line amongst all the possible lines, the one line that maximizes the margin between the positive and negative patterns. And if you maximize this margin, it's equivalent to minimizing the probability of error in a future case. Another important characteristic of support vector machines is that they are trying to solve problems which are not linearly separable in lower dimensional feature spaces by applying the so-called kernel tree, which is equivalent to mapping the data into a higher dimensional feature space. See the first example, where we have a simple linearly separable binary classification problem. It is easy to draw a line that separates the class of positive patterns from the class of negative patterns. That's an easy problem. Suppose now that you have another binary classification process where the class of positive patterns is mixed within the region of the negative patterns. Here it is obvious that you cannot draw a line, you cannot estimate a simple linear model that discriminates between the red points and the blue points. You must learn a more complex model to discriminate these regions of red and blue dots. Support vector machines to tackle this problem within the setting of linear functions by implicitly mapping these data into a higher dimensional space. Suppose that somehow this line begins to curves so that the data acquire a two-dimensional presentation. In that case, there is a line that discriminates between these two classes of patterns. And of course, these may be generalized to problems of higher dimensions. So the general idea is that the original input space can always be mapped into a higher dimensional feature space, as the one appearing in these figures. Here we have a two-dimensional feature space where once more you cannot draw a line that separates the blue dots from the red dots, but if you somehow map this data into a three-dimensional space, then you can have the equivalent of a line, a hyperplane in three-dimensional feature space that separates between these two classes of patterns. So finally, as I said in the beginning of the first part of this presentation, I'm going to present a comparative study of classifiers, each one of them addressing the problem of sentiment classification. We are particularly focusing on the economy and banking industry, where we have as a training set a set of about 9.5 million of tweets, and each tweet is represented according to the TF-IDF feature vectorization technique with 400 feature vectors. You can see that the positive class patterns, the ones that appear as blue dots, is about half the size of the corresponding negative class patterns. Here you can see a three-dimensional representation of these 400-dimensional feature spaces after applying a statistical technique which is called principal component analysis, PCA. It's a technique that you can use in order to reduce the dimensionality of a feature space for visualization reasons. As you can see, it's a very complex mixing of positive and negative patterns where there is no hope of separating these two spaces with just a simple linear classifier. So, as our classification results depict, the support vector machine with a Gaussian, the radial basis function kernel, is the one that outperforms the rest set of classifiers. For the given training data set, we reached an accuracy of 91.7% for correct classification, and the classifiers that were close to that was the random forest with 10 and 15 these numbers. Accordingly, multi-layer neural networks were quite close, but very hard to train, very complex models, very time-consuming models. And other approaches, such as the radial basis function networks, these are single-layer neural network machine learning paradigms, naive Bayes and classification via clustering were significantly worse in addressing this pattern classification problem. So I will leave the stage to Stavros, who is going to give you some ideas of how all these theoretical notions are incorporated by Ismuth and its context. The stage is yours. Thank you.
Hello, I'm Stavros. I'm sorry if I'll be a little bit nervous. It's my first time presenting. So, I am the lead software engineer for Ismuth. At Ismuth, we have developed the technology where we gather data from various social networks such as Twitter, Facebook, blogs, and forums, and save all this data to Elasticsearch, a NoSQL distributed system which provides us performance queries and aggregations. Also, we save all our aggregation and analytics, also and our training data set to MongoDB. All the supervised algorithms such as SVM need training. So the most important thing is to collect the data set, the training data set. At Ismuth, we have developed a simple UI where the trainer, the user, I mean, who will annotate the data, can see the text, read the text, and then annotate it in terms of industry, objectivity, and sentiment. There are some questions, such as which the correct data set, or how many data we have to train. The first question, we have to say that we should gather data from various time periods and various data channels. How many? It depends on the pre-processing state. If we have very good pre-processing states, we don't need so many documents to train. At Ismuth, we train 12,000 documents for its model. The next step, and very important step, is the cleaning. We have to keep only the...
I'm so sorry to interrupt, but I think this is quite important. Can you tell us what each model is there in the previous slide?
Oh, sorry. The model, we will discuss later about the model. Okay, let's continue. No, thank you. Well, the cleaning process is very important because we have to keep, from the text, we have to keep only the important words where tell us if the sentiment is positive or negative. So, two basic steps we have to follow is to remove the stop words. And another step is to stem the word. I mean, keep only the lemma from a verb, for example. Well, the next step we have to do is to vectorize our data. I mean, to transform our data from a raw text to the vector space. There are two steps the first step is the training step, where we have to import the data from our training data and clean data, import them to the vectorizer, then calculate the IDF weights, and then persist the model. The same steps are followed by the SVM classifier, where we have to add the labels that we gathered from the training process. At the testing stage refers to the new document, the unseen data. Well, here we import our unseen data to our vectorizer, and then calculate the TF-IDF weights. Then load the SVM model, import our vectorized documents above, and then do the prediction process. Here we see an example about how visualization works. At the training stage, for example, we have 3 tweets. If we feed this document to our vectorizer, we have the following representation of our data, where the columns are the unique terms of our corpus, and the rows are the actual documents, the tweet, for example. If we create our vectorizer model, this is called model. Then, if we want to know about the TF-IDF weight from the new document, we have to vectorize it, and then we see the weights that the new document got. If we analyze our documents, if we classify in order to have the maximum accuracy at our sentiment, we firstly decide if the document is objective or subjective, and if it's objective, we see the polarity. The same will apply if it's subjective. In order to have the maximum accuracy to our data, to our analytics, we have created multiple models for each industry, such as economy, telecom, IT, etc. All these complex analysis is provided to our customers in a simple, user-friendly, and interactive web platform, the Input platform, as you see here. We use detailed diagrams in order to visualize our aggregation and our data. Also, word clouds. And in order to have the maximum of performance, we have the high-end server-side technologies such as Python server, Elasticsearch, and MongoDB. And in order to have interactive and user-friendly front end, we use Symfony, AngularJS, and Bootstrap. Our next steps is to move our algorithms to a distributed infrastructure in order to do batch and streaming data processing. And our next step is to add more resources, such as new social networks, for example, use Snapchat, Pinterest, and more. Thank you very much.
I think we'll open the floor to some questions first. If I could kindly ask the speakers to repeat the question so that people in the live stream and everyone in the audience can hear. Okay. Any questions?
So, for instance, you ask for feedback from your customers to train for that subcategory and use the data given by all your customers to train the model.
The question is whether we ask our customers to pre-label the incoming data with an industry label. No, this is a task which we in-house perform. We separate our data sources according to the industry, and each particular set of documents pertaining to a particular industry corresponds to a different SVM classifier. This is done for two purposes. One which relates to the feature extraction process, the corpus vectorization process, to be industry dependent, and the other one, the classifier, the learning model, to be industry dependent. In such a way we can increase the classification accuracy of our system. If we would suppose that you have a tweet in the economy and banking industry where it says that we should burn the banks, and this is in the space of anarchy, would be good news. On the other hand, on the banking industry, it would be extremely bad news. So we take into account the context of the tweets. Yes?
So my question is of more theoretical and academic interest. Have you performed experiments on whether traditional NLP pre-processing tasks such as word senses ambiguation, collocation extraction, and such things, how these steps impact different classifiers? Because you showed us a figure where your classifier seems to perform better than the other ones. But it wasn't clear to me whether you have performed the same pre-processing tasks there for all classifiers. And the second question is, since you mentioned that you work with social media data, how does the TF factor affect your results, since social media data tend to be rather short, right? So TF, I suppose, is mostly 1 or 2 for tweets or even Facebook posts. Have you ever performed such measurements?
I will try to answer your questions, and if I don't remember them, you will repeat them. So the first part is that all classified on the same basis. Okay. So it is the same text pre-processing process which is followed. Okay. We haven't tried yet such more complex NLP techniques. We believe that for the purposes of sentiment classification, the standard unigram, bigram, or trigram techniques are effective for solving this problem. As I mentioned earlier in the presentation, in the course of the presentation, there is the problem which relates with the curse of dimensionality. If you apply more complex text representation techniques such as n-grams, this increases the size of the dictionary. Increasing the size of the dictionary means that increases the dimensionality of the feature space. So if you have a feature space with 10,000 dimensions, 10,000 terms in the dictionary, it means that you have to have exponentially larger amounts of training data. So there is a you have to control, to balance these two competitive tasks: efficient representation and efficient training of classifiers. But of course, these are things that we're going to experiment with in the near future. And you have to repeat the second one.
The second one. You mentioned, I think, that you're using TF-IDF, right?
Yes.
And from my knowledge, TF in social media data, especially tweets and Facebook posts, and these are rather short documents.
Yes,
these short documents, I guess that TF plays some role, yes, but I don't know if TF is a strong signal for this data. So my question was whether you have experimented with how much TF helps you.
Yes, we haven't done any experiments on this subject yet, but I will try to answer your question from a theoretical point of view. When you have a small amount of text, 140 characters for Twitter, for example, there is a probability that a few rather small disjunct of words will actually fire up in the vector representation. So you are dealing with the problem of sparsity. You have a very sparse representation. So this is something that you cannot avoid. It's an inherent problem when you need to vectorize to mathematically represent contextual information. I don't know, maybe deep learning techniques where you feed these sparse feature vectors into deep belief networks or convolutional networks may reduce the dimensionality, and you may acquire some more compact representations of your data, but these are open research issues, so you can write a paper. Okay, any other questions? Yes.
I didn't get the textual level on which you try to apply sentiment labels. I mean, if we keep in mind only tweets, this is easy. A tweet can contain one, maximum two sentences. But I think I saw you mentioned also blog posts, or am I mistaken?
No, you're correct. So
in a blog post can contain several hundred sentences. So which is the unit, the textual unit on which you go and say, okay, this is positive, this is negative, this is neutral? Do you go sentence by sentence? And if yes, how after that you combine all this stuff to give the label to the document?
After we vectorize this big text, we choose the best features in order to fit them to the SVM vectorizer. We don't just pick the first sentence. We pick the most important terms. There's a possibility to make a mistake. It's very difficult to handle posts with multiple sentiment labels on it.
So you fit the whole document as a bag of words, actually.
Yes, and choose the best terms.
Thank you.
By best, sorry. Just it was a comment. By best terms, what do you mean? Most represented or?
What? TF-IDF, yes.
Okay.
TF-IDF.
Can I ask something related to the models, because this was the question I asked earlier. So you have different models for different industries.
Yes.
Okay, so my question is, do you, when an incoming tweet comes in, do you have prior information for determining which model to use, or do you have another classifier to figure out what domain and therefore what model you should be using?
We have built a classifier where tell us in which industry the specific post is contained. At our platform, the users can choose in which industry his project contains to, in order to have the maximum score at the sentiment accuracy.
this is mostly done on a keyword basis. So the industry is a set of keywords that the user, the customer, the brand, the company defines a priori. It is given as input. Yes.
How come we include also the neutral as a case? I mean, are all posts either positive or negative?
Let me give you an example. Of course, that's not the case, but how we handle neutrality. As we mentioned before, support vector machines work by trying to determine these best optimal hyperplanes. So what is actually outputted by the SVM classifier is a soft decision value. This soft decision value may be interpreted in terms of closeness or distance from the boundary. So the more distance you are from the boundary towards the positive class, the more sure you are that this is a positive tweet, and vice versa. So if the soft decision value is quite close to 0, which means that it relies on the boundary, then this is a neutral tweet. And you may interpret these outputs in terms of probability. So if the probability of each class is equal, then you're also legitimate to make the decision that this tweet is a neutral one.
I understand this approach, but I don't fully understand why you don't consider the neutrality as a distinct class. I understand that SVMs work, as you said, to identify the best decision boundary between two classes. However, you can use the one versus all approach and always decide if it is positive or not positive, negative or not negative, neutral or not neutral, or, for example, the pain point that you asked.
Yes, you need the combinations of three
exactly.
two
Iron
classes.
Irony, and then choose the highest ranked probability about it.
That's another possible. We need to acquire classification results and high quality classification. Yes,
always like 4-by-9 classifiers of choosing the highest rank.
yes, but that reduces the overall accuracy.
Actually, you have experimented.
Yes, we have experimented with that, but reduces the overall accuracy.
Can I ask a
Yes.
follow-up on that?
Yes.
When you're training,
Yes.
does your training set also contain neutral examples?
No, it is a
That's
strictly
usually-
binary classification problem. Otherwise, you should employ this one versus all classification approach.
Yes, what I mean is, say a tweet comes in and I can't label it as positive, neither can I label it as negative. It's a neutral tweet. Do you discard that tweet?
I do not discard it. The output that the algorithm gives,
Not in the prediction phase, in the training.
in the training phase, they are discarded.
Wouldn't including more classes in the training phase reduce the imbalance problem? And
Would it increase it or decrease it?
decrease it. And if you include more classes, the distribution of probabilities for each class will be.
I'm not quite sure about it. I think that then the case would be that the majority of tweets will be neutral, because most of the time people are not opinionated or polarized concerning a particular subject. They only replicate news, or they are just saying something which is truly neutral. So I do not think that it would in some sense improve the class imbalance problem, will alleviate this problem. Yes.
And how do you deal with the imbalanced problem? Using cost sensitive or?
We have experimented with both ways that we pointed out. The first one is to explicit it by taking equal numbers of positive and negative patterns, and the other one is to assign a larger misclassification cost on the minority class. If you see the mathematical formulation of the SVM, you may assign two C costs values, one for the one class and the other for the second class. So if you increase the cost which relates to the positive class of patterns, then you balance the problem. You're trying to alleviate this problem.
So you're using both techniques, and which one outperforms the other one?
Yes, that.
Which one? The cost-sensitive approach or the resampling approach?
The resampling approach.
The resampling, and the resampling that you are doing, it's subsampling or upsampling?
It's a subsampling. It's an undersampling technique because we cannot replicate the tweets. We cannot generate.
You can generate.
There are indeed such techniques for yes, you're right.
There are
some techniques, yes.
Yes.
Smoother and Rasmus and all this stuff for artificially oversampling the minority class.
Yes, I know these techniques, but you see what the problem is. If you somehow exploit the geometry of the space to replicate a point within the same feature space which is close to it, and you make the assumption that it is a positive tweet, but this point may be not a valid document. I don't know if that would work.
It's a trick. It's a trick. It's like taking think about like modeling the distribution in the area of the documents and populate according to this distribution. It's like a trick in order to deal with the imbalanced class problem.
Okay, we can try it, but
yes,
my question a priori.
I wanted to ask you that the classification accuracy is much more greater if you are using resampling techniques over cost sensitive. Have you measured the difference?
We haven't done this.
You haven't done it. Okay.
But this is future work, so
okay.
We're mostly doing business, not research. Okay, these are very these are very difficult problems to address.
I have one if no one else. So so related to this, another approach might be, and I was wondering if you have any take on this, would be instead of the oversampling approach, is to use semi-supervised approaches. So because this addresses the problem of finding actual documents that you can use, but of course they're unlabeled. So have you considered doing something that's semi-supervised and taking other tweets that people haven't labeled and using something like code training or something like that to extend your model?
That's a possible solution. We haven't tried that yet. You could also use one class trying to model only the positive class and classify as negative everything that deviates from the model of the positive class. But all these are open issues, so you have to really provide a big amount of effort in order to answer all these problems. So, yes.
I haven't been understanding yet the presentation, so maybe you have already answered this, but are you using a linear or an RBF kernel, and why?
It is an RBF kernel.
For both tweets and deals?
Yes, for every model is an RBF kernel. According to the theory, when you use an RBF kernel, it's like implicitly mapping your data into an infinite dimensional space. So in the original dimensionality of the feature space, the classification accuracy is significantly lesser. This is, you may see that result in our table, where the SVM linear classifier is significantly for this particular data set. Okay. Any other questions?
Time for a less technical question.
I'll go for one because there's a bunch of pizzas waiting for us. You are going to be the person holding it.
Thank you. I was wondering if you have observed, certain textual terms are globally bloomed, regardless of the industry, and as a dual of that, you have observed industries that tend to go together with the same terms. I mean, whether certain combination of industries get to have the same output of the certain terms.
The same dictionary.
Yeah. So, for instance, automobile and oil industry may go hand to hand, for certain times. I mean, like the example of anarchy and banking you said, but something, more realistic, more less trivial, so that post-analysis could take place.
That's an interesting approach. I have to admit that I learned more things than you apparently have learned. So experimentation is the only answer to this question. I don't know beforehand. There may
This?
yes.
Are you setting that, we can do that together?
Okay, no problem. Okay.
Okay, thank you, Ismail.
I hope.
All right, so we'll take a break to eat, and then we'll come back to our second presentation. Right. So, thanks to everyone who stuck around. I know we did go a bit off schedule, but without any further ado, let's open the floor to Ferial. Angeliki. Go.
Hello, I'm going to talk about Ferial, which is a platform that converts hotel website visitors with personalized marketing. And why does it do that? So we have the online travel agents, that is aggregator companies, data aggregator companies such as Booking.com or Expedia, that charge huge commissions on the hoteliers. For example, if I want to book a night and this night costs 100 euros, then the 30 euros will go to the OTA, that is, he will get the mass commission, and the 70 will go to the hotelier. This means that the hotelier is going to lose this 30 euros, and if I stay for 3 nights, he's going to lose 100 euros. So what we want is to bring back this sum to the hotelier's cashier. Now, the travelers, including myself, book on the OTAs because it is more familiar to them and it's easier to use. So what happens before a hotelier decides to use our service? Travelers that want to travel, for example, and have a business trip to New York from Amsterdam, then they will also see the same information on the OTA and the hotel's website. And travelers who want to travel to New York for family trip, then they will again see the same information. So what we do is we personalize the visit of the user, and now the user sees tailor-made information on the hotel's website. So, for example, now if I want to have a business trip in New York, I'm going to see different information on the hotel's website, while on the OTA, I'm going to still see the same information with a person that wants to have a family trip. But the person who wants to have a family trip will also see again different information on the hotel's website. Now, what is our competitive advantage? There is a huge market on the travel industry, including data aggregator platforms, meta search engines, for example. Companies like Kayak has recently been bought by Priceline. Priceline owns Booking.com, for example. Kayak is a company that aggregates data for hotels, for example, or flights. So what they do is they price comparison the trips, and then they offer you certain packages. And same thing goes with Trivago, etc. What is our difference? Our difference is that we take into account the 5 stages of travel as designed by Google. So Google says the following. It says that, for example, I want to go on holidays during the carnival period now. And do I want to go to Greece, like Rehoboth, ski or pattern or something, or do I want to go abroad like Venice or Switzerland to ski maybe? So this is my first circle on thinking, where am I going to go? And then I decide that my friends can join me to ski here, so I don't want to go to Venice, and being there last year was too packed, so I'm going to Switzerland to ski. And where am I going to go to stay, and with whom? Who wants to join me? Are my friends going to have the same dates as me, some days off or not? And this is the second stage of the funnel, and then we decide and we narrow down until we reach to the very specific hotel product that includes the packs, that is the people who are going to stay there, the kind of hotel we're going to stay. Is it going to be a ski resort, or we're going to stay, for example, in Geneva and then travel for a couple of days to ski, or what are we going to do? And the perks. The perks are the offers and the discounts that hotels make to the users, by users and the travelers, the visitors that stay there. So some discount on the pool or a free breakfast and so on and so forth. So if we take, for example, Google Ads. Google Ads says you're going to have now 20% off for next month in this hotel, in Hotel X. I'm not even sure if I will have holidays, if I want to go there, if I even want to go to this country or something. So I turn. When we say that the user turns, means it doesn't buy this product. So we offer this. How can I say this? Let's consider this as some homocentric circles. So the broader information and the most generic one is given on the first circle, and then we dive into it. Now we have deployed a two-dimensional approach. That is, we take into account the funnel stage of the user along with his or her expenditure margin. What does this mean? For example, suppose that I do not have a lot of money to spend while I'm traveling. So what do I do about this? I want to stay in a hotel that is next to the metro station in Athens, and I want to just take the metro from the airport, give €6 and arrive at my hotel. Because I'm Chinese, I don't speak Greek. These Greeks are always on strike. I don't know how to get the transport things. I don't do public transport or whatever. But then there is another person, and he's, let's say, from New York, and he wants to have a business trip, so he has a higher expenditure margin and he doesn't have time to spend. So this guy is going to be here on the expensive segment, and he wants to just have an airport shuttle like we see there, and he just wants to have his taxi take him from the airport and straight to the hotel, and then from the hotel drive back to the airport when the trip is over. This guy can afford the €100 it costs to come and go to the airport, so he's not interested if the hotel is next to the metro. He just cares if there's an airport shuttle, and he still doesn't want to mess up with Greek taxi drivers. What's that? Do they even speak English? I don't know. I just want to get it over with. I don't want to get it done. So this is a slight example of which comprises both the expenditure margin and the final stage of the user. We can also some other examples here. I can use this thing to show maybe it doesn't work. This yes.
Try it.
Okay, let's see. Can I get? No.
It's the first button.
First to the left, right.
Oh,
yeah, it's here. Okay, yeah.
Did you find it? Okay.
So, for example, the chief user wants to know if his hotel will have free Wi-Fi, while if he can afford it and he stays at Hilton, the expensive user doesn't care. He just cares if there's a pool at the hotel. He doesn't care how much it's going to cost. So, what is our technology? Our technology is really simple. We're a software as a service company. So the hotelier just adds a few lines of code here on the hotel's website, and then this is the JavaScript, and we got some code here to booking engine. Booking engines are third-party providers. So when I click on a hotel's website and then I type in my date, I'm transferred to another company that is the booking engine, and it gives me the availability. That's where I can make my reservation upon. So we collect data from both these websites, and then we aggregate them and we analyze the behavior of the user, and we apply some machine learning algorithms in order to define which profile wants to see which banner. We serve our information embedded on the hotel's website. So like you've seen before, there is a window here showing the information pertaining to the user profile. So let's have a small example of our input data. This is a simplistic approach today I'm explaining, and just to show you how we want to replicate the notion of funnel. So suppose we have these prices. We have this is average daily rate. The ADR for some users is 430 euros, for some other users 341, and so on and so forth. So we have users here that have used Mac and Chrome, and have stayed on average 50 seconds on the hotel's web page. So all these users have here booked a room that costs for one night 432 euros. And then we have these other users that have paid something like 154. So now I want to define my last clusters. How do I give to my classifier the they want to input the data? Because sparse here we see only some of the data we're processing. These are hundreds of columns. Sorry. So our features are hundreds and maybe more, depending on what kind of aggregation we're doing to the data, how deep we dive into the ontology, or how high we want to approach it. So here, this is a quite high-level approach I'm showing. And so I want to know, do I define my users like users who have the ability to book an expensive room, a very expensive room, a cheap room, a very cheap room, or a medium or slightly medium? Or do I just want to have three, let's say, classes? For example, here we have three classes, expensive, medium, and cheap. But how do I know whether this pertains to expensive and this one? And why isn't this one pertaining to the expensive class or this one? So what we are doing is I'm showing one clustering approach. So this is the K-means clustering. Let's see what we are doing with the K-means. So what I want to do is define my centroids. How many here are familiar with the centroids approach in the K-means clustering? Okay, so quite a few. So working. So I'm defining my centroids here. So for example, here I have defined three classes. One is here below 50 euros, one is here below 100 euros, and the rest go up here. So I want to pull my centroids as far as I can, one from another, so that I can be sure that I will get it. And then we recalculate the model. So let's take this example. We have, for example, 45 euros per night and 59 euros and 152 euros. Like we've said, we have now three centroids. Now, let's see what's going to happen. We say we want to take clusters to partition all the data points. That is cheap, medium, expensive. Like here, I've shown you before. We have here the three clusters. We're trying to see what's going to happen, train the models, and here we have it trained. I'm sorry. And we have the positions. The positions is like we've seen the $50, $100, and $150. So our goal is to cluster the KI that is cheap, medium, and expensive to each data point. Our data points mix of I is the $45 per night, the ADR I told you before, or going to cluster it to $50. And why? We're going to see this right now. So we have to find the positions on our space where 1 or 2 or 3K, now we have defined that we want to use 3Ks, that's cheap, medium, expensive in our example. And we want to minimize this Euclidean distance between the data points. This is like the RBF kernel we talked about in the previous presentation. So what we want to do, what we want to find is get the argmin. This is the minimum distance of what? Of the Euclidean distance of our data points, that is the $45 per night, and its distance, that is the $50. Now, all these are considered to be in C. Ci is the set of points that belong to a cluster. For example, in the cluster 50, we have 5 instances. That is, 5 people are close to buying this product that costs 50 euros. I'm sorry, $50 is an example. So these 5 people have 5 vectors. Each time I see each vector, I assign it to the class of $50. That's what we want to achieve, but that's what we're going to see at the next following slides. So let's have an example. Now we have a centroid, $50, and we want to subtract it and have the square difference. So this is the Euclidean distance, and that's 3 squared 9, which is smaller than if we have the same x to x of I with the m of I being 79. That is the other difference, and this gives us 32. So now we see that this cluster is assigned here because the difference is much smaller. And now we have constructed our data. This is the table we were seeing before. We have now constructed our data and we're ready to fit our classifiers. So what do? Like we said before, our competitive advantage is the funnel of the users. So we have relational data. If a user here has an expensive behavior at one point of time, maybe he's going to change it. So for example, we have some, let's say, tablets that we find and say this is expensive. If a user uses Mac, he's probably quite affluent, but maybe then he changes because it was his friend's Mac, and he wants to use his own now or his mobile or something. And if a user, we've seen from our data that users that book on weekdays are much more affluent than users that book at weekends. And all this information. So our model changes and the user behavior and the funnels change at the course of time. So what do we do this? In order to be able to grasp this information, we need relational data approaches. And this brings us to our following slide, which refers to how we apply classification. We have two types of models. We have the generative type of models and the discriminative ones. What is the difference? The first types of models describe the joint probabilities. So, for example, here I can have A and B. So I just multiply this and I have the joint probability of A and B. So these two are not dependent on each other. While the discriminative models we're using to replicate our funnel, we have the conditional probability. That is, we try to find what these two have in common and then we divide it with our state, let's say here in Markov models. So here we can see that the generative models of their naive base, when we have to assign a vector to one class, and when we have more than one classes, that is in our case, we apply the hidden Markov models approach. So these are generative models using the joint probability. While in the discriminative models, we have the maximum entropy. And for one class and for multiple class problems like ours, we use the CRF. So why do we do this and what are the differences that have led us to this decision? Let's to the naive Bayes algorithm and how it works. So here we have the probability of a class, one class, given a vector, a feature vector. So the probability of this class is the how do we call this word in English? I forgot about it. Product. It's a product. So this is the product of each of feature association given the class. Let's take an example in our case. Suppose we have one of the class expensive users, and now we want to see if this expensive user uses Mac and Chrome and stays on average 5 seconds on the page, then we want to see if what is the probability of this user being expensive, and then we calculate this equation, and we get the probability of Mac given being expensive and Chrome and the 5 seconds, and then like we've said, we have the observation, the state itself, the Y. And then we divide it with the evidence. We don't really care about that, so we don't take it into account in our own example. So how do we get these numbers? I'm driving back to Marx we saw before. So we have here this example. Now we have expensive users. We have this information from our clustering, like we've said before. So here we have in total 1,000 users, 500 expensive, 300 very cheap users, and we have another 200 users that we don't know whether they're expensive because they show they have this behavior. 50% of them uses Mac, and 0.75 uses Chrome, and 0.25 uses stays on average of 5 seconds on the page. So I want to see, are these users very cheap users? They buy very cheap rooms, or do they buy expensive rooms? So we calculate the probability in this probability matrix of every instantiation. So for example, here we have, like we've seen, we have 400 users out of the 500, 400 of the 500 who use Mac. So this gives us 0.8. And then all these users, out of these users, 300 out of the 500 use a Chrome, etc., and so on and so forth. So I won't go through the whole matrix now. And this is how we get these scores. So this is the first score we saw, 400 divided to 500. And then we have our very cheap vector to calculate probabilities. So we have the very cheap, and here we see that there is no very cheap user who uses a Mac. So here we have a 0 probability. So given that we're after the product, there is no user here with 0 probability. And then we have our unseen points. We want to calculate. We calculate it the same way as before. And we have this evidence. So, I'm sorry, we have these results. And we see that this result is closer to this result than to 0. So probably these users are closer to expensive, or are expensive users, and they do not belong to the cheap cluster, or class in our case. Now let's move on to the hidden Markov models. What is the difference of hidden Markov models and the naive-Bayes algorithm we showed before? Like we've said, the difference is that now here we have a multiple class approach, and we have a directed graphical model. When we have graphical models, we have models that we calculate their probability. So this is and their transition here. We have this hidden state. This is the state of y of I, and it depends on the previous state, and then the previous state depends on the previous observation. So these are our observations. This is whether the user has Mac or Chrome, or how many seconds does it stay. This is he expensive or isn't he? Why does this restrict us as a model? Because, like we can see here, our class, for example, the expensive class, depends on the previous knowledge only. And this is not our case, because we have topics, for example, we said Mac, Chrome, expensive in 5 seconds, that do not pertain only to the expensive segment. And then we have others that might also pertain to the expensive segment or not. So we cannot only depend on the previous one, we want to depend on all other previous user behaviors and models. So this is how the directed graphical models work. So let's see, like we've said, we have the hidden probability here and the observable probability here. The observable here, and we do not take into account this probability. Like we've seen, we take the probability of this state given its previous state and Mac given that it belongs to the expensive segment. So these are the distributions we will calculate. Again, the probability of x of I. So over the initial state, this is our hidden state, and then we have the transition probability, and we have then the observation distribution, that is what we've said before, like if the user who has Mac is an expensive user. And now the learning takes place, and the inference is done with Viterbi alignment. And now we want to see why we end up using discriminated models. So we have the maximum entropy model. So the difference now is that we factorize our data, and this gives us this result. So this is the normalization function. I'm not explaining it here. So we have this normalization factor that depends on our input factors and the parameter cell. L is the weight of each feature function, and we'll learn it upon training. So these weights change of how important is to use, for example, this probability or the other probability for each x input we have. And then we have our feature function here. Now, our feature functions are a pair of output labels. Now we have the x minus 1 and the xi and the xi plus 1. And we have our input sequence, and we have the current position every time with respect to which we want to jump back or go in front to see what the user is doing. If he has seen the pool first, or if he has seen the garden, that's a different behavior than if the user has seen the shopping list of the hotel, or if he has if he wants to go and have an excursion. If we have the opposite behavior, first he sees the excursions and then he sees the pool, then that's another. This is a different behavior, because most probably all users are going to see the garden of the hotel. So that doesn't tell us anything. That doesn't tell us anything. What is important is to follow the whole funnel of the user. So here we have an undirected graphical model. So before we had the arrows, like we've seen on the hidden Markov models, and here we have the arrows that lead from here, from this observation, we go here to this class, and this class leads us here, given this observation. Now we don't have this, we don't have arrows. So this means that our model does not depend anymore only on its previous state. We rather take into account potential functions. These are some factorization, as I have explained. Again, we calculate, here we see the state we are. This is the hidden state we have and the previous state, and we have our L calculated weights and the feature function here. We also calculate our joint probability for a class given a certain state. And let's have an example on how we apply this. So we have here some probabilities, and let's see what this shows us. We have again our three classes: expensive, another guy who is expensive, another guy who is cheap. Now let's see, this is the representation we fit the classifier with. Let's see what's happening. For example, we have for each feature, that is one feature, each xi that is mapped on our feature vector. For example, we have x1, x2, and x3. So each feature vector is mapped on one class. For example, Mac Chrome and 5 seconds is mapped to the expensive segment. Here we see Mac, where we have question marks. It means that we do not have any information for these features. And then all feature vectors, here we have 3 feature vectors who segment our funnel, are mapped on one instance that is for every user profile. So all this thing here is one user for us. Like we've said, the comments might be hundreds, and here, of course, maybe again hundreds of classes, maybe a bit less than the comments. So a lot less actually. But anyway, so here we see the path of a certain user. This user uses Mac Safari. He stays 5 seconds on each page. So he's assigned on the expensive segment, and then he uses Mac and Chrome. He changes his browser, but yet he still stays for 5 seconds on each page on average. And then he uses Windows. So maybe he has changed his device. He uses his phone now, and he still uses Chrome, and he stays 2 seconds. But this is this goes to the cheap segment. And let's see what is the sliding window. We want to take advantage of the ability that conditional random fields give us, that we can infer the class given the user's previous actions. What does this mean? It means that the more data we feed it, the more complete each state of the equation becomes. So let's see here an example. Here is our x of I. If we check these points, then we take as well the back and the previous moves of the user. Here we do not have any input. This is the user's first move, so these are all question marks. And then we have Mac user and Safari, the same thing as above, but I couldn't fit it out here. And then we shift our window. And now what we see here is that this user has made this. The classifier has tried to dealt with this, and now he's going to our next feature, Mac. So now our user is using Mac, and he's using Chrome, this one, and then we're processing this feature here, 5 seconds, etc., and so on and so forth. And we consider this being the end action of the user. Of course, the users make hundreds of moves. So this is what we do in order to be able to capture the user needs and be able to offer the user the correct product, the correct funnel stage he's at when he's trying to book a hotel room or a lot of hotel rooms if he wants to stay with his family or his friends. And I would like to thank you for your attention, although it's too late and probably most of you have things to do. And this is our site, and this is my mail.
Okay, do we have questions?
I know that for illustrative purposes you put all those kinds of variables, but actually on a day-to-day basis, what kind of variables are you actually using? And how many would you take?
Like I said, for example, let's go here. Here, for example, this vector, this is the x vector. Like we see here, might be our n might be 800 or 700. A lot of variables. I don't know.
I'm not sure I really understood the full model of this slide that you So here,
Mm-hmm.
but if I understand correctly, it's node on Y depends now on the previous state
Not
and on
only
X.
here.
Yes.
Y depends on this and on this. And
So if it depends on two states, it's not Markovian anymore, is it?
no, it's not.
So how do you do the training? Because you cannot use Viterbi anymore as you used previously. It doesn't have
No,
Markovian
we
properties
don't.
anymore.
We do it this way, like I've explained here. So we take the exponential feature functions here and we multiply them. So this is the sum now. We do not do the product like we were doing in the Viterbi level, for example, or we do in the base. So it's too complicated maybe to explain this right now, but this is what we take here. These are the factorization I've tried to explain here.
It's like a neural training.
Exactly. You can see a second for
I have a question. So both in hidden Markov models and conditional random fields, you have there's this notion of structure. So the ordering in which you organize the various Ys is important. So how do you decide on the network, the organization of the different features you talked about? Because you talked about the funnel, right? How do you order them in the sequence?
For example, I don't know if I understand this correctly, but we have a user that makes a move on the hotel's website and he sees, for example, the pool of the hotel. And then he makes another move and he sees, like we've said, the garden, for example.
Right.
So I think the classifier with these things, condensed, because what we've said in the clustering, for example, with k-means, goes for everything. I mean, we have thousands of browsers versions where all these things are clustered, and we cluster categorical data and things like that. So we pre-process our data, we cluster them, we have our basic clusters. Accommodation is, there are 100, 200 types of rooms. You cannot fit them all on a classifier. The data are really, really sparse. So we cluster them and then we feed the models.
Okay.
I don't know if I replied to this question.
So the clusters, the features are the different clusters that you have here.
So our feature, for example, here, let's see something easier, maybe here. This might help more. So here, this is one feature. This is X1, and this is X2, and this is X3. And this is here we can see this is X, this is X1, X2, X3, X4, and backwards.
Right. So what I don't understand is the order in between these.
This is
the order plays a role, right? The matrix of probabilities that you're going to do, the different distributions that are at each node, depend obviously on the actual structure of the underlying sequence, right?
Exactly.
So how do you pick whether you're going to put, because one is what computer they're using, and the other is what browser they're using. Why does one come first and then the other one?
Because that's how they're written on their database. So we get one row of the database is one move, and it has this, let's say, Mac Safari 2 seconds, and the second row has Windows Chrome 5 seconds. I didn't represent it very well here. This is more of a naive-based representation. So every row in the database is followed by another row until we have the whole funnel of the user. And that's what we input the classifier and the clustering.
Now that's also brought on the k-means. How did you decide on the number of clusters? And why did you choose k-means and complementary clusters?
So we've tried more or less a lot of kind of clustering data and expectation maximization because we had sparse data. So the problem is that, like we've said, the hoteliers do not trust their proprietary sales channel, their website, and they're not tech savvy. So they say, okay, I'm going to trust all my rooms on booking.com, so nobody buys on their website. So when we first started working on that, we had 5 bookings per month on a hotel's website, and that was really sparse when you like 3,000 or 4,000 at least bookings, gold vectors to train your models. So we couldn't have all these classes. We had hotels where one night was 6,000 euros, and hotels that one night might cost 50 euros. So we had a lot of outliers. So we said, let's just group it like that. So we do not, we try and error all the time. This is just a small example, but we started with 3 or 5 classes at first because simply we didn't have a lot of data. And then you just try to train your k-means or whatever you decide to train, and you see where your major clusters is because you visualize this as well. So you can see the number, remember C, I told you the number of instances in each cluster. So you keep the strong clusters. Yes.
Can you please explain a bit the business behind that? I haven't understand exactly
The business model.
the business model. What I'm a hotel owner, and what do you do?
So you're a hotel owner, and we say, do you want to use our service? And you say, why? And we say, because if you allow us to personalize the experience of the user and give different information on each one. So for example, a person who's doing, like we've said, a family trip is going to see different information here than a person who is doing a business trip. And you say, why should I do this? And we say, because it's for free. So you just add, like we've said, 2 or 3 lines of code on your website, in your booking engine, and that's it. And we do the rest. And if we increase your revenue, then we get a 2% on the extra generator revenue we offer you. If we do not increase, of course, you decide to leave. And okay, we haven't lowered any hoteliers, don't worry, income and revenues, and that's it.
So in other words, you suppose that the client has to come to the hotel site. Okay, you don't.
The end user, exactly.
The end user must go to you to the hotel site that's your client.
Exactly, because at first we were only operating in the booking engine, so we had our offers here. But like I said before, nobody books on the hotel's website. So no matter how good our personalization was, nobody could see our product because visitors would turn here. I also had a slide, I didn't put it here after all, explaining only this path the user does from Google and the meta search engines and everything to arrive here on the hotel's website. And then we got out of here and got here on the hotel's website because we wanted to be visible, because not a lot of users visited this site. And now we want to go outside and maybe become a lead generator or provide personalized advertising. So that's another step.
Okay.
But we don't do it right now. Yeah.
So if I understand it correctly, what you're offering the hotel is that you're offering to increase their conversion rates, right?
Exactly.
Okay. I have another question. Let's focus on the user. How do you track me as a user? I mean, do you build a profile about me specifically?
No. We have this, like what we said, we know that profile 1, for example, is Mac Chrome something.
Yes, what I don't understand is how you showed us earlier that for a certain user, you know that on day 1 he connected using a Mac and Chrome.
Yes.
How do you understand on day 2 that it's the same user?
From the cookie. And this is a problem that is not solved globally. Not even the user has solved this. Unique user identification. This is because I may erase my cookies if I am here and then I use my mobile phone. I don't have a cookie. How do you know it's me? And so this cross-screen problem is an industry problem across e-commerce. Personalization and recommender systems like Amazon.com or Facebook, when it proposes friends and everything, suggest friends. They're never 100% sure that this user is this user, for example. So this is a global problem.
But do you have information in order to understand that I'm using the phone and after 5 minutes I've used my Mac? Do you have information to?
Exactly. There are companies that address such issues like Lotame, which is a data aggregator platform, or Drawbridge, who's all these companies specialize on online advertising and personalization and recommender systems, or Amazon even does this, and Google and everything. But what they do, and what we do actually, what everybody does when you're working on e-commerce is the following. You can see from your data which user is who, more or less. For example, I will give you a simplistic example. If I see a certain IP and a certain move on a hotel's website, let's say, for example, from the US, most probably, and then I see another one a few seconds or a few minutes later, most probably it's the same user. And because we've seen that users who have one cookie make more dense moves and then they stop. So this is a way to infer that this is one user. You see, if he comes from New York, for example, it's not very possible, but in a small boutique hotel in Mykonos, on, I don't know, March, a lot of users come. So we try to all the time learn better and better how to identify the user. And we haven't made it yet, and nobody has actually, because it's very difficult. You just do inferences like that. And with devices, if he has a Mac, he's probably using an iPhone, and he's not the guy that I saw the Windows source, or things like that, you know.
So you are putting, just a question again. So you are putting like banners in the websites of the hotels.
Exactly.
Something
so,
like that, advertising banners that change.
It's something like that, yes, that you see here. In fact, I haven't. I have it. No, here, for example, this is the hotel's website. So here you can see some information about the hotel. For example, unfortunately, I forgot to put one to see the actual banner. There you can see. So I don't know if there's anything more.
Okay, super. Thank you very much.
Thank you.
That's it. Thank you very much to our sponsors, Pulpfish and Alba. Thank you for making this possible. Have a lovely evening. Tweet us. Also, please feel free to connect with me and PM me on meetup.com if you want to share feedback or ideas. I will actually organize a more structured process for you to give us feedback about the meetup in general when you guys want to take this. And that's it. Enjoy the rest of your evening. Thank you very much, and thank you to those of us who watched us on the live stream. Bye-bye. Good night.